All right, in this video, we're going to be working through more redox questions. We're starting with questions 16, 17, and numerical response question 7 that all have to do with the diagram of this zinc carbon cell. Here's our diagram. We have a carbon rod, a zinc case, manganese 4 oxide, and a moist paste of aluminum chloride. Here are the half reactions in this cell. The zinc becomes the zinc ion and 2 electrons. This is our oxidation. I'm just going to label it right away. This is our oxidation, and I use my acronym that the loss of electrons is oxidation at the anode, and this is the reducing agent. And then our other half reaction is that we have this manganate reacting with, or manganese 4 oxide, reacting with our ammonium and 2 electrons to become manganese, that'd be manganese 3 oxide and ammonia and water. This is our reduction because our electrons are on our reactant side. So here's our reduction. And we know that the gain of electrons is reduction at the cathode, and it's the oxidizing agent. The value for the cell potential difference, the E naught cell, is positive 1.50 volts. If we have a positive voltage, then this means this is a spontaneous reaction. Spontaneous, and it's a voltaic cell. All right, let's answer some questions. The zinc carbon cell is an example of what type of cell? Well, we just answered that. It's a spontaneous reaction, so it's a voltaic cell. And the moist paste of aluminum chloride allows for the flow of what? All right. A lot of the voltaic cells that you may have seen, or diagrams you've seen before, will have a salt bridge, and then they'll have a wire, and then they'll have liquid electrolytes. This moist paste of ammonium chloride that we have here, I said aluminum, the moist paste of ammonium chloride, this is our electrolyte. The electrons in a cell are forced to flow through a wire in order to, in a voltaic cell, harness the energy of those electrons from this redox reaction. So this is not where we want the electrons to flow, but instead this is going to help us balance the ions so that the reaction can continue to happen. So the statements above are completed by the following information in the row. This is, first of all, a voltaic cell because it has a positive cell potential difference, so it is not C or D, and the movement of ions happens in the electrolyte, not electrons. We're going to want electrons to flow through a wire so that we can run them through some sort of load and use those electrons to do work, use this reaction to do work. The cathode in the zinc carbon cell is made of what? And when the cell is operating, the electrons will flow what? All right, back to the diagram. Zinc is where our oxidation occurs, and the oxidation reaction occurs at the anode. So zinc is not the cathode, it's the anode. This is our cathode reaction, which would be happening at our other solid cathode, which is the carbon rod. So carbon is our cathode here, not the zinc, and electrons always, in both electrolytic and voltaic cells, flow from the anode to the cathode. The cathode is where you have your reduction reaction happening, so you're going to have to supply those electrons at the cathode. So C is our answer here. This is always true for electrolytic and voltaic cells, so this is never true. Electrons are not going to flow from the cathode to the anode unless you're like recharging a battery, in which case you're flipping what's the cathode and what's the anode, rather than making the electrons go from cathode to anode. The electrical potential E for this half reaction is what? Okay, well, we know that the overall cell potential is positive 1.50 volts. And the way that you would find this normally is you would take the reduction cell potential for the reduction half reactions of the cathode, and you would subtract it or subtract the reduction cell potential for the anode to figure out what the net cell is. What we're looking for is this half reaction. This is our cathode half reaction. Again, we know it's the cathode half reaction because it's the reduction half reaction. And we know it's the reduction half reaction because the electrons are on our reactant side. And our anode is the zinc half reaction. We can find the cell potential from our standard table right here for our reduction potential for zinc. So we're going to scroll down till we can find our zinc reduction reaction, which is right here, negative 0.76. I'll zoom in a little bit. So we know that our positive 1.50 volts equals our cathode half reaction potential minus our negative 0.76 volts. This is from the redox table. And it's the zinc half reaction. And so we're just going to add this over to the other side. So we'll do plus 1.50 volts. And then we're going to add a negative 0.76 volts. The signs are important here. And we will end up with a positive 0.74 volts is our electrical potential for this reduction half reaction. 0.74 volts. Which makes sense. Really what you're looking at when you're looking at this table, you're looking at the difference between where your cathode is and your anode, and the space between those two is the cell potential. So 0.76 all the way up to positive 0.74, we can see clearly that we're going to have our oxidizing agent above our reducing agent, which is zinc, and that the space between those, the gap, would be positive 1.50 volts. Next question. The amount of ethanol in a person's breath can be measured in an electrochemical cell. The relevant half reaction equations are given below. Methanol plus 4 protons plus 4 electrons, this is not methanol. That would be acetic acid becomes ethanol and water. And then oxygen plus 4 protons plus 4 electrons becomes our water. Here's our two reactions. They're not given to us in the order that you might be used to in the redox table. In the redox table, you go from a higher electrical potential on the top down to a lower electrical potential on the bottom. If you look at these, you'll notice that this half reaction here has our larger electrical potential, which means that if we were to rearrange these on the redox table, this would actually be higher. This is our higher one, so it's going to be our cathode. They're trying to trick you by putting them in this order. This has the higher E0, therefore it is the cathode. It's the stronger oxidizing agent, it's the reduction. So the half reaction that occurs at the cathode is going to be reaction number 2. If you look at reactions number C and D, these are oxidation half reactions. These would happen at the anode because they have the electrons on the product side. These are oxidation half reactions, which would happen at the anode. So you could eliminate those. And then between these two, we know that it's reaction number 2 because it has the higher cell potential. And if you were to actually arrange these like they are in our redox table, you would have your strongest oxidizing agent being reaction number 2. If the reference half cell were changed from the standard hydrogen half cell to the standard cadmium half cell, then the reduction potential for equation 1 would become what? All right. I like to imagine that really what the cell potential thing is that we have a building that can move up and down underground. And really what you're measuring is your distance from the ground floor. So the normal hydrogen cell is 0.00 volts. This is our normal hydrogen cell. And this is based on the normal hydrogen cell. Based on the normal hydrogen cell, the reduction potential for this is positive 0.58 volts. That's our normal reading here based on our hydrogen standard cell. And the cadmium half cell from your redox table, if you find the cadmium half cell right here is negative 0.40 volts, so below here. The cadmium one is negative 0.40 volts. But if the ground floor were to shift so that this basement floor is now the ground floor, this would become 0. So you have to know how far away are these from each other. Kind of, if you're taking physics, this is kind of like a vectors question where you're figuring out what's the distance between these two. We're going to find that simply by subtracting from our new reference, or subtract our new reference from where we were. So we want to figure out what this distance is. We know that the distance from the ground floor up here is plus 0.58. From the ground floor to the basement is negative 0.40. What's the distance between the two? So we'll do that by a subtraction. So we'll subtract our negative 0.40 volts because this is becoming our new standard reference, which will bring us to a positive 0.98 volts. It is now higher off of where the ground floor was if we take this and we move the basement down. Now it's higher. That's my analogy. Hopefully that's somewhat useful. So the distance between those two is positive 0.98 volts. When you have a new reference cell question, really what you're asking is how far away are you from that new reference? Now we have a cell stoich question. If a current of 4.00 times 10 to the negative 3 amps is maintained for 10 seconds in this electrochemical cell, then the mass of ethanol that reacted, expressed in scientific notation, is A.BC times 10 to the negative D grams. All right, this question is a lot more work than the previous two multiple choice questions, but we're going to work through it. First of all, we're asked to find a mass of ethanol, so we're going to need to know our molar mass. So our ethanol, again, C2H5OH. So to find our molar mass, you're going to do 2 times 12.01. That's the molar mass of carbon from your periodic table. We have 6 hydrogens, so 6 times 1.01. And we have 1 oxygen, so 1 times 12. So our molar mass of ethanol is 46.08 grams per mole. I want to find, I see that it's stuck behind my face. There we go. I want to find mass of ethanol. That's the unit I want, is grams. So I'm actually going to do this in a unit cancellation cell stoich way, not using the formula. The one thing I am going to need from my data booklet, there's not formulas given to you in this data booklet, but Faraday's constant is there, which we will need because we're going to have to convert between coulombs and moles of electrons right here. So I'm going to set up my unit cancellation first with the unit that I want to end up with on top, which is grams of ethanol. Grams of C2H5OH. I have 46.08 grams of ethanol per mole of ethanol. Now, I have to figure out how I can go from this to just grams. So what can I cancel with moles of ethanol? Well, I have a reaction here, and I'm using this reaction here. I have 1 mole of ethanol for every 4 electrons. So then I'm going to go back down here, and I have 1 mole of I have 1 mole of ethanol. I'm going to do that in purple to show that I'm canceling that out. 1 mole of ethanol, which I'm going to put in the numerator so that I cancel those units, for every 4 moles of electrons. So now I have 46.08 grams of ethanol for every 4 moles of electrons, which is some progress. But I don't want moles of electrons. I need to cancel something with moles of electrons. I can use Faraday's constant to cancel out something with moles of electrons. I know that I have 9.65 times 10 to the 4 coulombs for every mole of electrons. I have mole of electrons right now in my denominator, so I'm going to have to put mole of electrons in my numerator and cancel it out with coulombs. 9.65 times 10 to the 4 coulombs. This will cancel out moles of electrons. So now I know that I have 46.08 grams of ethanol for this many coulombs. Now I can cancel out coulombs because I have amps. An amp is a coulomb per second. So I can multiply this by 4.00 times 10 to the negative 3 coulombs per second. This will cancel out my coulombs. Now I'm left with grams per second. So I can cancel out my seconds of ethanol. I'll use purple again with my 10.0 seconds. All of my units will have canceled at this point except for grams of ethanol. So what I'll be left with is just grams of ethanol. I'll pull out my calculator and run through this calculation here. Basically, I'm just going to divide by the things that are in the denominator and multiply by the things that are in the numerator. There's my calculation from a previous thing. So I'll do 46.08. That's my molar mass. I'm going to divide by 4 because 4 is in my denominator. And then I'm going to divide by, and I'm going to put this in brackets because sometimes the scientific notation, it's nice to keep it all together. 9.65 times 10 to the 4, because it's in the denominator, that's why I'm dividing. Then this one is in the numerator, my amps, so I'm going to multiply by 4.00 times 10 to the negative 3. I'll also put this in brackets because I like having the scientific notation in brackets in my calculator. You can do this in different steps. You don't have to do it all in one, but I'm showing you that you can do this calculation all in one go. And then my 10 seconds is also in the numerator, so I'll multiply it by my 10. What I'm going to be left with is this number here, which rounded to 3 significant digits, because that's what they're asking me to do here, is going to be 4.78 times 10 to the negative 6. 4.78 times 10 to the negative 6 grams of ethanol, which on the numerical response sheet would be entered in as 4786, because this is A, B, C, D, according to the way that this is written. I'm going to stop the video there.